All right, everyone, welcome to today's webinar with RFMW and Marki Microwave. My name is Katie, and I will be your Global Spec moderator, and you are just hearing my voice right now. Now I would like to introduce you to today's presenter. With us today, we have Nikki Mobtaker. Nikki is an application engineer with Marki Microwave. So welcome to today's event, Nikki, and with that, I'd like to pass things along to you to get us started. Go right ahead.
Hi, everyone. Thanks, Katie, for the introduction. I would like to take a minute and thank RFMW for co-sponsoring this webinar with us, with Global Spec. And let's get started. Today, we will be unlocking RF amplifier performance. In this webinar, we will talk about advanced and overlooked biasing techniques. Imagine you're working on a new design, and you just received a promising new amplifier, a sleek little QFN package, and a detailed datasheet promising excellent performance. Your task? Integrate it into your system and see if it truly delivers. So, you head into the lab, ready to start characterizing the amplifier, but right away, there's a problem. You've got the QFN, a datasheet, and a handful of hopes, but no evaluation board. Your buyer didn't order one. No big deal, right? You're a skilled RF engineer. How hard could it be to design a quick DC bias and evaluation board? Famous last words. All right, so what does an evaluation board need? Let's start with the basics. Proper 50 ohm input and output traces. We have to make sure we have a solid match, or all of that sweet RF performance we were hoping for will go straight out the window. With that taken care of, now we just need to get some DC into this amp. Quick and easy. Just hook up VD and VG, and we're back into the lab in no time, right? Well, this doesn't look anything like the datasheet. Where's the beautiful gain and flat response we were promised? Instead, we've got mismatches, ripples, maybe even oscillations. Something's clearly off. Let's take a closer look at this response and figure out what went wrong. All right, first problem, this nasty low frequency gain spike. What's going on here? The datasheet showed a nice flat gain response, and this is unusable. The amplifier needs a proper low impedance path to ground at this frequency. Without it, we get uncontrolled gain peaking, and that's not what we signed up for. Next up, look at this ripple. My gain curve is far from the flat, predictable response I expected. And that's not just measurement noise. It's real instability creeping in. Something in our design is letting unwanted signals contaminate our response, and we need to track it down and nullify the source. And just like that gain spike, return loss is looking ugly. That means poor matching, reflections, and yep, more performance degradation. Our quick and easy biasing approach is coming to haunt us. Anything else I'm missing? Oh yeah, we take for granted that our VNA is DC blocked, but in the real world, that's not always the case. If your load isn't DC blocked, you could be in for a nasty surprise here. So what's the root cause of the mess? A suboptimal DC bias and poor evaluation board design. All right, let's take a step back and look at the big picture. On top, we have our first attempt, a simple, bare bones evaluation board with a poor DC bias design. And as we saw, the RF performance suffered because of it. Now compare that to the board on the bottom. It's more complex, sure, but every component is there for a reason, and the result is a clean, stable RF response that actually matches the amplifier's datasheet specs. So, what makes the difference? A properly designed power supply and bias network. Over the next 40 minutes, we'll break this down step by step, why each component in the design is needed, what it does, and how to ensure optimal biasing for any given amplifier. We'll cover the most common pitfalls, how to avoid them, and use real-world design examples throughout to tie it all together. Let's get started. As a system designer and amplifier user, you don't want to think about amplifier operation, and you certainly don't want to think about amplifier application circuits. Ideally, the only external connection needed for an amplifier chip is its power supply. So why do we need external components? Why can't all of the circuitry be included on chip? We at Marki are always trying to make our amplifiers as easy as possible to use, but there's a few things that cannot always be included on chip. Firstly, low frequency content, signal or noise, are required to be treated with larger value capacitors and inductors that can reasonably be included on a 4x4 millimeter package, say. Therefore, we need external components to isolate power supply noise from contaminating your output RF signal. All power supplies besides batteries include parasitic AC transients. This is low-frequency noise that can only be eliminated with larger capacitors than could fit on chip. Ideally, we would want the power supply to be a one-way connection to the amplifier. Unfortunately, this is your signal's world, and we are just living in it. What can happen is your signal can leak from your amplifier to your supply or bias rails and cause fluctuations or ripples to appear at the output. And this brings us to our first troubleshooting example. So you're running your amplifier output through a spectrum analyzer, and you see a lot of noise near your signal. This signal is not pure enough for, say, the radar system or sensitive modulation system you are trying to implement. Panicking, you run the amplifier through the phase noise analyzer in your lab, and indeed, you see about 20 dB more close-in noise than what you were anticipating. What's the problem here? It may be supply rail noise. As I said earlier, AC transients can come from a power supply, and RF spurs can leak from your amplifier back in the supply line. The noise that presents on your supply line directly feed into your output. We need to mitigate that noise, so the best solution is to implement a bypass circuit in your supply rail. The eval board components we recommend on our data sheets are valued to AC ground disturbances, so the least amount of noise can leak into your signal. So you implement the bypass circuit, analyze your new results, and you can take a sigh of relief. The close-in noise you saw earlier has been attenuated by 20 to 30 dB, and your boss never knew there was a problem to begin with. So we just covered why we need to isolate power supply from your amplifier and amplifier from your power supply. Now imagine if we have multiple bias or power supply pins. This opens up opportunities for external feedback. Under the right circumstances, this feedback can lead to oscillations that can majorly degrade an amplifier's operation. Finally, for broadband amplifiers that operate from megahertz to multiple gigahertz frequencies, external circuitry is required to extend the low-frequency operation. Now that I just told you almost all the ways surface mount amplifiers can fail without the right external components, the good news is that Marki amplifiers are designed such that all of these functions can be accomplished with a few well-chosen components. Later in this talk, I will explain how to choose these components to optimize the operation of your amplifier. So stick around. On to our second troubleshooting exercise. Your purchase of the AMM 9181 PSM has just arrived when you go to the lab to verify its flat gain response and low return loss. But from the performance plot shown, there is an unexpected spike of gain and return loss at low frequency. With distributed amplifiers, the circuit architecture commonly includes an input transmission line feeding the gates of the transistors following a 50 ohm termination load. An AC termination is required after the load to ground the leftover signal power that can return back into the input line. For high frequency, small capacitors can AC ground well, but this won't work for lower frequency input signals. Bigger capacitors can attack these disturbances better. Therefore, off-chip components need to be implemented. And that is what we recommend on our application circuit for the ADM 9181 PSM, capacitors on the AC ground pins. The VG rails also have these capacitors for the same reason. And below are the results for following our advice. The return loss and gain flatness significantly improved and matches the datasheet specs. So this brings up a reasonable question. How do we choose components we recommend? Let's start with capacitors. Here is the ideal function of a capacitor. An ideal capacitor has impedance that is inversely proportional to frequency. At low frequencies, it is high and it decreases until nearly zero. A real capacitor, however, will contain inductance within its leads and capacitive sections. This creates some problems. Firstly, your capacitor no longer looks like a capacitor at higher frequencies, meaning the impedance is high when we wanted it to be continuously low. The other problem is that the inductance and capacitance creates a self-resonant frequency where the impedance of the capacitor is at its lowest. This can cause glitches in the electrical performance of your amplifier. A way to flatten the response of the capacitor at high frequency is to implement another shunt capacitor with a higher resonant frequency. That way, you have a low impedance for a broader range of higher frequency. Now let's look into what these capacitors are used for and how we work with the issues I just reviewed. Most power supplies are DC to DC converters, meaning instead of providing a constant voltage that you set, they switch the output voltage between 0 and maximum supply and create an average with duty cycle and frequency to provide the voltage wanted. So your supply contains a low frequency, which is called power supply switching noise. A big capacitor is required for that disturbance to provide a low impedance path to ground, and we call that a bypass capacitor. Visiting an earlier issue, RF spurs can couple back into your supply line. Even low frequency RF inputs are usually higher than the supply switching frequency, so we need an additional low impedance path to ground. We implement decoupling capacitors to do so. And you see from the plot above that the impedance remains low for a longer frequency range. Lastly, the input signal to your amplifier may come with a DC offset. This can mess with the bias voltages we recommend for the amplifier. Also, within the amplifier, your signal gets introduced to offsets for biasing purposes, and DC at the output may be an issue to other components in your system. DC blocking capacitors provide high impedance to DC without impacting your signal. This will level out your signal to 0 volts offset. An issue that presents with bias/supply lines and external shunt capacitors is that they are also connected to internal or on-chip shunt capacitors. The connection between the two include a wire bond and board trace that contains some inductance. This together creates a CLC, capacitor inductor capacitor network, that resonates at some frequency, creating a high impedance spike at a path where we would want continuous low impedance. This can heavily affect the electrical performance of the amplifier. In particular, the gain profile will be impacted by this resonance, which we will see later. So we need to flatten that impedance spike out. So we add a resistor to dampen the resonance and lower the overall quality factor of the resonator. We call this resistor a snubber. And as you can see on the plot, this reduces the impedance spike, but it also increases the overall impedance of the rail, which may degrade high frequency operation. So there is a balance to the value of this resistor. We don't want it too low to ineffectively snub, and we don't want it too high to reduce high frequency gain. Consequently, we value these snubber resistors usually low, around 5 to 10 ohms. On to troubleshooting exercise 3. This example came from one of our product engineers' observation of the initial characterization of the AMM 9619 PSM. The amplifier was designed for 2 to 26 gigahertz operation, but we wanted to know what was causing this huge 600 megahertz gain suckout. So let's take a closer look at the interfaces of the QFN package. There exists an on-chip capacitor, a bond wire, and an off-chip capacitor connected to the output signal through the power supply, or VD. The components listed created a CLC network combined with the RF signal set at low frequency, and you can have a resonance on your hands. And an impedance spike occurs from this resonance, which creates an obstacle for your power supply path, starving your amplifier of power and creating a momentary gain suckout. To solve this problem, we implemented a snubber to DQ that resonance, lowering the obstacle for power to reach the amplifier at resonant frequency. Typically for these snubbers, we value them by calculating the square root of the inductance over the capacitance of the resonant circuit. And for the final results, this is what a snubber implemented and valued correctly looks like. The spike is non-existent, and the high frequency performance did not suffer. We have wrapped up the capacitor portion of this webinar. Now let's review inductors and their on and off chip relationship. With capacitors, their on and off chip forms have a similar parallel plate operation. Contrarily, on-chip inductors have a completely different form and are vastly inferior to the inductors that can be realized off-chip. Off-chip inductors are typically cylinders or cones of ferrite material with hand-wound wire to create high values of inductance. On-chip inductors are horizontal metal spirals with no ferrite core. Only very small values of inductance are achievable because of its build and properties. For this reason, amplifiers that have a higher power, higher current consumption, and/or broadband amplifiers that operate below 2 gig and above microwave frequencies of 6 gig require off-chip inductors for their operation. This off-chip inductor is usually added at the output of the amplifier, since it needs to supply current into the drain or the collector of the transistor. Whether on-chip or off-chip, however, all inductors have limited current capacity due to their finite series resistance. The wire size can be increased to reduce the resistance and increase the current capacity, but this makes the inductor physically larger and reduces the entire inductance value. Worse than this, there is a parallel capacitance due to coupling between the windings of the inductor and capacitance to ground due to proximity of the inductor to the ground plane. Because of all of this, the equivalent circuit for an inductor is a real mess. Methods for modeling and compensating for realistic inductor behavior would take an entire webinar or an entire book. These issues are handled by our designers when the inductors are on chip, but if an off-chip inductor is required, it can be a major challenge to create a functional power supply circuit. These inductor issues typically lead to resonances or suckouts in the amplifier gain and return loss. For this reason, Marki manufactures and recommends small form factor surface mount bias tees that include a DC block and the power supply inductors we just discussed. We offer two different surface mount packages. One type is the BTM, or mini bias T. Its manufacturing includes machine-built components and a carefully designed filtering circuit to minimize resonances while offering broadband performance. The other type, BT, uses hand-built inductors to remove most resonances and offer higher current and power handling. Both are small form factors and offer the benefits of pre-characterized performance, with each unit individually tested to ensure optimal electrical performance. Marki strongly recommends the use of package bias Ts over customer-designed bias circuits, since such circuits create unknown performance effects in our customer systems. This brings us to our fourth troubleshooting exercise. This brings us to our fourth troubleshooting exercise. This example was brought to us by a customer that was experiencing oscillations at the output of the ADM 8007 PSM with or without RF applied. Displayed on screen is the repeated setup results with no RF applied. The application circuit shown was the customer's implementation. They shorted pins 8 and 10. We explained on our data sheets that pin 10 serves as the DC supply for the amplifier's input stage, and pin 8 serves as the DC supply for the amplifier's output stage. After some tribulations, we were able to realize that there was a feedback loop between the stages. Oscillations were traveling from the output stage to the input stage through this shorted connection. And it was receiving gain from the amplifier and the nonlinearity. That's why oscillation power was pretty high, it was around 7 dBm, and why there were multiple harmonics of the fundamental. Even when we tried using separate supplies, oscillations were still occurring because the traces coming out of the QFN were too close. So the solution was to disrupt the path of the stages altogether on the supply rail. By implementing an off-chip inductor of 420 nanohenry between both supply lines, we created a high impedance path for those oscillations. Even a single supply will not allow the monsters to rise. Now we will discuss the details of transistor amplifier biasing. Before we discuss the components, we need to make a brief detour to look inside the amplifier and understand what's happening both on and off chip. This diagram shows the basic operation of a transistor amplifier. At high frequencies, the transistor acts like a very fast variable resistor, routing current either to the output load or to ground, depending on the small signal input. To achieve this high frequency operation, we need to set up the DC operation of the transistor in a specific way. The first thing we need is to block the DC from going either to the RF input or output with a DC block. Next, we block the RF from the power supply with a component usually referred to as an RF choke. Typically, we use an inductor for this purpose because it provides a low impedance for high DC current of the power supply. A resistor can be used, but the voltage drop would be greater for that reason. The final step is to add a bias voltage or current to the input. As we'll see soon, the transistor has certain input ranges where it works well. So we need to bias the transistor to this point at DC. We need an RF choke between the bias source and the input signal. Because the current is typically low for bias inputs, we can use a medium value resistor here, like hundreds of ohms, or an inductor. In a real amplifier, we would also use tuning elements to stabilize and set the operation band of the amplifier. Now we will look at what voltage or current we want to use as the bias set point. The basic operation of a transistor is that as you increase the input voltage, either by increasing the bias voltage or the input signal, the current draw of the transistor also increases. At low or very negative input voltages, the transistor is completely turned off, also known as pinched off. And at high input voltages or saturation, the transistor is at maximum conduction. If you set the bias point in the middle of pinch off and saturation, or the linear region, this will give the most linear change in transistor current with input signal, and therefore the most linear output signal. This amplifier is known to be Class A. If you set the bias point lower or slightly above pinch off, the transistor will be off for part of the cycle of the input signal. This reduces the current consumption and overall power dissipation of the amplifier, but it means that the transistor will not respond for part of the cycle of the input signal. This causes distortion to the output signal. This type of operation is called Class AB amplification, and it results in an output waveform that looks similar to a half-wave rectifier as shown in this time domain plot. There are two common types of field effect transistors that Marki uses to realize amplifiers. Depletion mode amplifiers require negative bias to operate and can exceed current limits with a grounded bias. This negative supply can be supplied simultaneously with the power supply, but beware of passive components in your bias path as they may cause delay. Lastly, depletion mode FETs have the highest transistor performance of the transistors we use, mainly because of the switching speed or frequency handling capabilities. The other type of field effect transistor that Marki uses whenever possible is the enhancement mode transistor. Amplifiers made with these transistors require positive bias that is commonly supplied on chip. They do not require sequencing, frequently include current mirrors, which I will discuss soon, but they do have lower transistor performance available compared to the depletion mode. One issue that arises in biasing transistor amplifiers is that not all transistors are made equal. Process variation and variation of temperature impact optimal bias points for an amplifier. While it is easier to bias an amplifier with constant external voltage, this will cause more variation in amplifier performance than if an internal voltage reference, as generated by a current mirror, was used. Constant current biasing, however, would provide a lower efficiency and output power. See, under constant voltage, your current is naturally increasing and decreasing with your signal cycle and input power. Constant current outputs the same current no matter the stimulus. Displayed is a histogram plot comparing gain variation of sample lots of a depletion mode amplifier, the AMM6702SM, that uses no constant current biasing, and an enhancement mode amplifier, the ADM9028 PSM, that includes a current mirror on chip. As you can see, there is still variation amongst both amplifiers, but the spread is significantly lower with the amplifier that has current mirror to set the bias point. Even with variation over temperature, the current mirrored amplifier would have less variation. So, depletion mode amplifiers have higher performance, but they require this pesky negative supply. One of the most common problems with this is that a customer will have a fixed positive rail and they may or may not have a negative power supply available. If you additionally have a fixed negative supply rail, the simplest solution is a resistive voltage divider to supply bias. However, this must be designed carefully, as we'll see soon, if no negative supply is available. Oh, I'm so sorry. Yeah. However, this must be designed carefully, as we'll see soon. If no negative supply is available, one can be created with the UC5 voltage sequencing circuit as shown and explained in its app note on our website. Finally, there are commercially available bias controller chips that create a negative bias and maintain a constant current on the amplifier. Generally, this is the best option for electrical performance as it will reduce the variation as we saw in the previous slide. But it is expensive and space consuming if you have multiple amplifiers in your system. This brings us to our last troubleshooting example. You've received a Marki depletion mode amplifier, the AMM7473PC, and the design for your system has a fixed negative supply of -5 volts. You are required to set the gate voltage to -0.65 volts while maintaining a fast turn-on time. The simplest solution you can think of is to throw a resistor on the bias line and use the value to set the output voltage. However, given the low gate current that the amplifier requires, this resistor would have to be large in value and precise to set the correct voltage. A consequence to this is a larger RC delay with the on-chip gate capacitors. Another option is to use a voltage divider to set the bias. Given the ratio of the available voltage over the required, it's roughly 7:1, which determines the ratio of your resistors R1 and R2. The benefits of the voltage divider when it comes to speed is that the R in the RC delay is now dependent on R1 and R2 in parallel. Given any two resistors, the parallel resistance works out to be roughly the value of the smaller resistor. Comparing this to the first solution we came up with, which was one big resistor, this voltage divider provides smaller total resistance. The trade-off to voltage divider and smaller total resistance, however, is that there will be more current draw. Now that you have the ratio and the vision, you can mess with different values and find the right speed. The top display shows a rise time of 45 microseconds if you squint, and the bottom display shows a 5 microsecond rise time. These two circuits output the same voltage, but the bottom topology is faster because you are reducing the circuit resistance by a factor of 10. If you are concerned with current consumption, however, the current is reduced by a factor of 10 with the slower circuit, as we discussed earlier. So, to wrap up this webinar, the next time you are receiving a surface mount amplifier and there is no evaluation board, you know better now than to characterize it right away. You will look back onto that data sheet you were handed earlier and read the recommendations for biasing. If the amplifier requires multiple supplies and/or an application circuit, you know the importance of these components. Without them, we can see all sorts of poor performance, such as unwanted clipping, suckouts, oscillations, gain and return loss spikes, you name it. And with the tips today, if changes needed to be made to the external circuitry that we recommend, you can alter with confidence. Thank you.
All right, Nikki, thank you so much. This is Katie from Global Spec. So we're going to move into our live Q&A session. So Nikki's going to take some questions from all of you. So Nikki, I'm going to pass things back over to you to do some questions from our audience.
Yeah, let me look at the questions here.
Okay, so I see one. Can you give more tips on how to detect oscillations from an amplifier? Yeah, so the easiest test is to not apply RF and see if there's signals at your output. If there are, and there's no input RF, that's definitely oscillations. Another way is if RF is applied to not check the spacing of the unexpected signals. If they are uniform and reducing in power, you're looking at oscillations and its harmonics. A way to tell without a spectrum analyzer is by observing the current consumption of your power supply. With RF on, there should be very little to no current variation. And with RF off, the current consumption should match the datasheet's quiescent current. If it's lower, it might mean oscillations are occurring and saturating with your amplifier to lower power consumption. Let's see if there's another question. Another question. How are DC blocking capacitor values decided? DC blocking capacitors are dependent of the signal you are applying. DC blocks are just bad low pass filters. So if you're applying a low frequency RF, you have to be careful of the impedance of the capacitor at that frequency. You cannot throw a big cheap capacitor on that line because your signal might be in the rejection band. At high frequency, the only concern with the value is its corresponding size. The value is not the only factor you should consider. You also want to purchase capacitors that have higher resonant frequencies, and you cannot forget the impedance match of the capacitor to your system. I see another question. I have some leftover diplexers. Can I use those instead of bias tees? You can, with a few things to look out for in your design. Firstly, DC current handling is greater with bias tees than most diplexers. So do check your current consumption. Another thing to look out for is the low pass filter response of the diplexer in relation to other frequencies in your design. If you have additional low frequencies, they can couple onto the low impedance path and modulate the output of the amplifier you are using. Leslie Smith asked, how does the bias circuit affect modulation, memory, and linear amplifiers?
Maybe like the low frequency path, very low frequency path.
We'll think about it and email back to you the response. Another question. Is there an advantage or disadvantage to switching the gate voltage instead of switching the drain voltage on and off? Is the gate voltage quicker? So that's actually a really good question. With gate voltage, you have a smaller change of current. This actually means a slower overall change, a larger RC delay. With VD or your power supply, you have a larger change of current. So the speed is much faster with that. But you have to keep in mind the speed of the current available. So like the power supply you connect to the drain, is it fast enough to make a significant difference in your speed and turn on time? So there's another one. Hello, good morning. I have a question. Let's say I need an active DC bias. Do the tips you just mentioned still apply? I mean, yeah. When I'm assuming active DC bias, there's some sort of amp or something, but
with DC bias, I mean, the bypass circuitry we provide are, again, AC grounds for those AC transients or any disturbances, really. Another question. Can you provide tips to make Amplifier as broadband as possible?
Broadband blocking caps, broadband bias.
Yeah, I mean, broadband bias tees are your best bet to have an extended, even performance throughout your frequencies. That's really all I could recommend. Another question is with inductors. I mentioned in the talk that inductors are placed on the power supply. Why are they there? Can we use a shunt capacitor instead? Well, with inductor power supplies, that's usually in a bias T configuration where you have the inductor to allow DC and to get rid of AC transients, and the DC block to block DC from your signal. Now, if you were to place a shunt capacitor instead of that inductor, what'll happen is your signal will come out of the DC block or before the DC block and will go to that shunt capacitor because it sees it as AC ground, just like the other AC transients. Let's see if there's any more questions. Is the UC5 available as a separate component? We do not sell the UC5 circuit, but in that app note, we go over the components we used, why the components are there, and it's a very helpful guide to make that UC5 sequencer. I'm just going to read this question out loud. Is there a relationship between bias current for your amplifier and the broadband bandwidth of your signal? For instance, will my biasing circuitry demand more current handling capabilities if my amplifier is operating with 10 megahertz of bandwidth versus 1200 megahertz, assuming that the amplifier is specified for such frequencies? I would say that I think it varies. Personally, like the data sheet will actually have these performances set out. If your broadband app actually does operate between 10 meg and 1200 meg, that insertion loss, all of that will be presented there. It's not, I don't think it is just like a only frequency issue. Why are some bias tees leaking current in the range of microamperes? What I think of automatically with this is just the parasitic losses of inductors and capacitors. Capacitors have mostly their losses through their dielectric. It's kind of like a resistance. You don't want electrons to flow through, but they can if your dielectric is a little conductive. So that's where that loss comes from. With inductors, we saw that there's all of this parasitic resistances and parasitic capacitors. They can also attribute to the loss. So that's what I think of when I think of leaking current with your bias tees. Does Marki amplifier datasheets provide the wire bond inductance and internal cap values so I can deduce the external stubber needed? We do provide that information when it's needed. Like we will say if it's important, the output capacitance or input capacitance, if it does affect external. You can always contact support and ask us what we recommend for wire bond sizes, or if you do have some sort of external circuit, we can always help you out and recommend things on your behalf. You mentioned current mirrors. How are they used? Current mirrors create an internal voltage reference, but the main thing is that their current is, current mirrors are like stages of transistors, right? And the current between those stages are actually a proportion, and you can determine if you want the proportion to be higher, like the current, you want it higher to the next transistor or lower. But this proportion also protects your current fluctuation. And that's kind of how current mirrors are used. And yes, we use them in enhancement mode amplifiers because we have that positive bias. Another question I have is, can you expand on the thermal relationship with transistor current? Yeah, so thermal concerns, we are mainly interested in junction temperature of the transistor, junction meaning channel path. Room temperature additionally affects that, but the main attribute to temperature is an increase in current flowing through your transistor. In circuit terms, that means the current isn't going to your load and it's flowing towards ground. Because of the properties of FET material, current consumption decreases with increasing junction temperature. And this phenomenon is called RF cooling. Transistors will typically have models or calculations for junction temperature, so you can best determine this. A side note, we also use HBTs, that's a type of BJT in some of our amplifiers, and they also have an opposite effect. So as junction temperature increases, their current also increases. So that can be very dangerous, and we do some circuit stuff to make sure it's okay. Yeah, I think we are all done with questions here.
Again, I want to thank everybody for taking time to attend today's webinar event. Nikki, thank you so much for being here. Take care, and we will speak with all of you soon.